In this video, we'll look at different types of junction diodes. Okay, so far we have looked at resistors. A resistor is a sort of a conductor which will allow electrons to flow. We also have what is known as an insulator, which does not allow electrons to flow. And in between is something called a semiconductor, which allows electrons to flow under certain conditions. Okay, example would be when you pass electricity or you connect them to a voltage source, they might start conducting. Connect to a voltage source. So here we will be talking about junction diodes are a type of a semiconductor. Okay, so one way of looking at this is through the electrons. So I know some of you have probably forgotten chemistry, but there's going to be a very brief thing I want to mention. This is how it looks at the atomic level. There's a conductance band and there is a valence band. So the electrons, which are shown as dots, can move to the valence band or so-called holes. So that is what happens when you connect a conductor to a power source or voltage source. So the dots are the conductance band. And the other one is the valence band. And this is a conductor. For an insulator, what happens is there are actually three bands. There is the conductance band, there is the valence band down below, and then there is an in-between band, which is known as the energy gap. So the gray band is the energy gap. Energy, and this is our insulator. So what's going on here is when you apply a voltage across an insulator, the energy gap prevents the electrons to flow from the conductance band to the energy gap, sorry, to the valence band. Now, semiconductors look very similar to the insulators, except that that valence band is pretty small. Okay, so it's small, and in normal conditions, the electrons will not flow. But if you have to do something special with it, like connect to it to voltage, so the electrons will flow. So when the voltage is very minimal, the energy gap cannot be crossed, and when the voltage is increased, they will eventually cross the gap. And now for semiconductors, what is done is that you typically add donor elements. So semiconductors formed by adding donor elements to silicon or germanium. So silicon and germanium are two elements of the periodic table. And by adding what are known as donor elements, you can create a junction diode. So what are these donor elements? So we have boron and gallium and another two elements from the periodic table. these have excess holes, and if you add them, this is called a p-type semiconductor. You can also add arsenic or phosphorus. These have excess electrons, and this is known as the n-type semiconductor. So these are the donor elements. Now let's look at how exactly a junction diode looks at the atomic level. And then we'll just do it for a little bit, and then we'll just think of it in terms of circuit symbols. Okay, so how do you create a junction diode at the atomic level? Okay, you take a p-type. This is, you take silicon, you add boron or gallium, and what that does is it creates these holes, because boron gallium has less electrons than it has holes, and so it creates a p-type semiconductor. And then if you connect it to an n-type conductor, which is formed by putting some arsenic and phosphorus to silicon or germanium, you have an excess number of holes. So, sorry, excess number of electrons, and I'll show a negative sign to indicate that there are electrons. So let's say that you take this to p-type and n-type, and this is just when it is attached. Okay, now what happens is the electrons like to go towards the holes, and what you'll see is after this reaches a steady state, that is, the electrons have traveled to the holes, you'll see that there will be a band here, and that band is will have the left side. On the right side we had electrons which are now flowing to from the right side to the left side. So we'll have some negative charge here. There'll be some positive charge here because the electrons have left, and so they'll create holes. And then this is our usual p-type and n-type with some electrons. Okay, so some electrons have flown from the right to the left, and what this has done is it has created what is known as the potential barrier. This is the potential barrier, and that barrier prevents more electrons to flow from the right to the left. Okay? And this potential barrier is typically 0.6 to 0.7 volts. And as I said, this is after this whole system has reached a steady state. Okay, so the diode, which we'll be talking about, is basically the thing on the right. It is basically a p and n type connected together, and it has reached steady state. Now, as I said, once you have a semiconductor, so this is the semiconductor junction diode, we can get this semiconductor to conduct under certain circumstances. Let's see what are the ways you can get it to work. I said voltage source is one way to do it. So there are two ways to connect this diode, which we'll be looking at very closely. Two ways of connecting the junction diode. One way is, well, let's just take that diode and then connect it such that the P and N. So let's connect the P to the positive end of the supply. And then the other one to the negative. Okay, now what's going to happen here is I did draw that there were some negative charge here when it had reached steady state. This negative charge will now try to flow through the circuit into the voltage source and then come out here and come back. Negative and then so the electrons are actually flowing this fashion. So you can see that electrons are flowing because of the voltage source. The positive end attracts the negative, and then that's how electricity flows. So this is going to be, in this state, this way of connection will ensure that the electricity flow and the diode is said to be conducting. So diode is conducting. Okay, now we can do the reverse, which is connect the battery the other way. So now this is connected to the negative. This is the positive. So we did have excess electrons on the left side. So this is P, this is N. So there are electrons. And this is positive. So now what's going to happen is, because this is connected to the negative end, this negative and the negative here will repel each other. And the result is that the potential barrier, which I talked about here, the small barrier here, will actually grow. And you'll have a big energy barrier growth. And that happens because we have excess electrons now in the p-type. They are repelled by the negative voltage. And so, and the same thing happens on the positive side. The holes are repelled with the positive side, so the energy barrier grows. And here the diode is said to be non-conducting. That is, there's no net electricity flowing in the circuit. Okay, so now you can think of the diode as something like a switch. The moment you apply the voltage, the right polarity, it lets electricity to flow. So if you have a bulb here in the circuit, then the bulb will light here, but here the bulb will not light by changing the voltage. Okay, now with that introduction, let's see how to represent diodes in circuits. The symbol for diodes is as follows: circuit symbol. Okay. The line, the vertical line, indicates that's the N, and the other side of the triangle indicates it is the positive side, the p-type. This is the p junction, this is the n junction. So clearly, if you want to have the diode conducting, then you want to connect the p to the positive end of the source. Okay, I did show you how the p-n diode works, but a better way to do this is to do it more systematically by changing the voltage. Just connect it to a voltage source and measure the current across it. And so what happens is, if you do that experiment, that is, you pass a series of voltages, positive, negative, and then measure the current, then you'll see that the voltage current plot, note that our current is on the y-axis, will look something like this. So here, on the right side, we have a very high current up from, for a voltage starting at 0.7. So this is basically the voltage barrier. The moment the current is, so the voltage is greater than 0.7, you'll see that the current just goes to its maximum value. Okay, so it's fully conducting. On the other end, we'll have almost zero. That is, the diode is non-conducting. And then at some point, it actually will go down here. So this is about 50 volt. And this is where the negative 50, sorry, this is negative 50. And this is known as the breakdown voltage. So what happens there is that you will basically, if you go beyond minus 50 volts, you'll basically fry the diode. It will no longer work. You'll damage the diode. So you wouldn't want to go to a great negative voltage. However, if you increase the voltage of positive value, some point of time, it starts conducting all the electricity. But you need to overcome this 0.7 volt gap, which is the potential gap, which occurs when you connect the P to the N. Now, this is what you'll get for a real diode. Okay. What people do is just to make life easy, they approximate the diode as follows. So the curve is approximated as this. Straight line. This is 0.7 volts. This is the voltage. This is the current. So they're assuming that instead of being this curve, it's just a straight line. So it conducts above 0.7, but does not conduct less than 0.7. So this is what is known as an approximation of the real diode. Okay, so you can use that, but in this course, for the problem I'm doing, I'll actually approximate this as there's another approximation which we do just to make our life easy, and we'll assume, which is known as the ideal diode approximation, we assume that the potential barrier is simply zero. And so we have a line like this way, where again, the same thing, this is the voltage, this is the current. And so you see that the potential barrier is assumed to be zero. So this is the ideal diode. That is, the diode conducts the moment you have positive voltage, and then does not conduct when there is negative voltage. Okay, so if you're told to solve a problem with the ideal diode approximation, you'll assume this curve. If you're told to solve the problem with the real diode approximation, then you want to use this curve. Okay, then give you slightly different values. Let's look at a circuit involving a diode. Okay, and this circuit is known as a rectifier. So we'll call this diode as a rectifier. It's a pretty simple circuit. We connect a voltage source to a resistor. That goes to a diode, like so. And we're interested in measuring the voltage across the diode. Now, why do you want a resistor here? A diode by itself does not have resistance, and you just don't want to put in too much current. Although I drew that curve with the current going to infinity in the previous plot, you really don't want to send a large current. So to limit the current, you put a resistor in series with the diode. Okay, so now we have this circuit, and the question is, if we send a sinusoid input, okay, like this. This is V in. Then what is the output? Okay, we need to figure this out. Okay, so this can be done by analyzing the diode using the same things which I showed you earlier, which is you need to think of that plot of voltage versus current. Here we have one plot and we have another one. We'll assume it to be an ideal diode and use that to analyze the circuit. So let's get started. Okay, so first what we do is we will assume an ideal diode. So assume ideal diode. Remember what that means is if you do a voltage current plot, you will get something like this. Okay, so the circuit, let me draw it here again. V in. V out. Okay, so let's do it. The easiest way to do this is to think of how will the diode, in what conditions will the diode conduct and which conditions diode will not conduct. Now the diode, since you assume the ideal diode, we can see that this is the positive end, this is the negative end, that's the P and N, and so it will not conduct when we have the positive attached to the negative, and it will conduct when the voltage reverses or this one becomes positive and the other one becomes negative. So let's just assume that V in is positive. And what that means is this positive is connected to the negative, so a diode is not going to conduct, and so the circuit will look like this. Okay, so the diode is not conducting, so it is effectively an open circuit. Okay, I equals 0, and then the question is, what is the output voltage? Well, if there's no current, the output voltage will be the same as the input voltage, because there will be no voltage drop across the resistor. So V out is V in, and that's pretty much it. Now let's do the reverse, which is what if V in is negative? Now when V in is negative, put negative. When this is negative, there's negative here, and you'll see that the diode is forward biased, or better way to think of it is positive. This is positive, and so the current will flow, and so that's effectively making the diode as a short circuit, or we can replace the diode with a piece of wire. So this circuit will look something like this. Okay, I've replaced the diode with a short circuit. Okay, now what? So this should be positive. Now what will happen is there will be a current. It will be V divided by R. And what will happen is that the net voltage drop will all occur here. So the voltage drop here, remember the current I is flowing through this. The voltage in the resistor will be I times R, where I is V divided by R, or V in divided by R times R, which is V in. And then the V out will simply be 0, because there is no voltage drop between these 2 points. There is just a piece of wire, and that wire we assume has no resistance. So V out is 0. And now, given these 2 conditions, A and B, we are now ready to make the plot. So the plot will look like this. V in, V in, and this is going to be V out. Note that what we found was when V in is positive, V out is V in. When V in is reverse or negative, V out is 0. So this plot will look something like this. V out is positive, V in is V out is V in. Okay. When V in is negative, which is here, V out is 0. And then again positive, again 0. Positive, 0, positive, 0. Okay, so that's it. So this is how the output look. And so this is how the diode acts as a rectifier. It rectifies the positive half and clips the negative half. Okay. Now that we've done diode, let's look at another type of diode known as a Zener diode. Zener diode. Okay. A Zener diode is a diode which is usually used in reverse bias. That is, it is very much similar like a junction diode, and junction diode looks like it's more used in the powered bias, but Zener is explicitly used in the reverse bias. The symbol for a Zener diode is as follows. Okay, so this looks like a Z, and it's the same, it has got the same meaning. This is positive, this is negative. So ideally you want to connect this in the reverse bias, which means you want to connect this negative to the negative part of the power supply. Okay, now we can make a plot of the voltage to the current, just like before. The voltage, current. Okay, so this is how the Zener will behave. Then it goes 0. Now at the reverse bias, it will actually be something like this. Okay. So this part is known as the VZ, or Zener voltage. And then this is our usual potential barrier, which is potential barrier. Okay, so what's happening is when you connect this Zener in reverse bias, when the voltage is the voltage, whatever it is, applied for a value up to the Zener voltage. If you increase the voltage any further, the input voltage increase any further than VZ, it'll regulate the voltage to the Zener voltage, which means that you can use the Zener diode as a voltage regulator. Okay, so you supply to the Zener, let's say the Zener voltage is, usual value is 5 volts. If you supply it with 10 volts, then it will clip the 5 and only send 5 volts to whatever circuit you put. So the way this Zener is connected is as follows. R okay, and this is our V in. This is now going to be the Zener voltage. Okay, so VZ is going to be constant. So this circuit looks exactly similar to the previous circuit. There's no difference except that I've replaced the diode, junction diode, with the Zener diode now. Okay, so we can do a similar analysis like before and try to make a plot of V in versus V out. Let's say there's a particular similar V in. This is our V in. positive, negative, positive, negative. Okay, let's do the V out. Okay, so now let's see how to analyze this. Now, for all practical purposes, the Zener diode behaves very exactly like a junction diode in powered bias. So Zener behaves similar to a junction diode in forward bias. Okay, so you can just think of it as a normal diode in forward bias. In the reverse bias, it clips the voltage to 5 volts. So that's what we'll do is this. We just make a IPV. We, instead of drawing the circuit again, we can just look at this one and see. So here, what's happening is in this first circuit, we saw that when Vn is positive, it's reverse biased, it's open circuit, and when Vn is negative, it is forward biased. So when it is forward biased, it behaves exactly like a junction diode, which means that for when Vn is negative, it will be a wire like this, and the voltage will be 0. So we can, just by looking at this, we can draw the voltage for the negative part. So we can go here and draw 0. It's 0 here to here. So we're done with that. Now, when Vn is positive, go back here, we see that when Vn is positive, the diode is reverse biased. Okay, now the reverse bias behavior, this says that the V out is V in. Now that's true for the junction diode as long as V out is less than VZ in. The moment it becomes greater than VZ, it'll actually clip it to 5 volts. So in other words, what we have here is positive, the same as V in, but this will happen only as long as VZ is less than is greater than V in. The moment VZ is less than V in, then we'll say clipping. So what we can do here is following. Clips goes here, clips. Okay. So this is VZ, Zener voltage. Okay, so clearly this is assuming that the Zener voltage is somewhere here, right? If the Zener voltage is reached, then it will clip. If, however, the Zener voltage was somewhere there, then you will not see any clipping effect. It will just be the normal sinusoidal. Then the diode is pretty much like a junction diode. But the moment the V in, there is the Zener voltage is below this amplitude, you'll see the clipping. So this is where the clipping takes place. And this is how it acts like a voltage regulator. Now, here's the issue. Could you use this for voltage regulation? You don't really use a Zener diode for voltage regulation, even though it does that. It's because it actually does vary a little bit, and the regulation is not perfect. So what you do is, if you want voltage regulation, you probably want to use what are known as a voltage regulator IC. IC is a better way to regulate the voltage. Okay. The IC is one example of the IC goes by the name 78 as per XX, where XX could be 0, 5, 12, 15, which means that it regulates voltage to 5 volts or 12 volts or 15 volts. So your power supply can be, so let me draw the IC here. Let's say LM78, it should be LM787815. So if you look at the spec sheet, it will say what are the input voltages are. So you can connect it to a voltage from 17.7 to 35 volts. This is your V in. Okay. So your power supply can be between that range. You don't want to go above that because that will damage the IC. And what you're assured is that the output is always 15 volts. Because this is a 7815 IC. Okay, it's a 3-pin IC. You'll see 3 legs. As I've shown you, one will go to the ground, one will be input, one will be out.